My name is Brian Osborne. I'm a senior principal consultant at Bioteam, and today I'm going to be talking about using your own data for AI. Primarily, we're going to be talking about creating neural networks. AI is obviously much more than deep learning or neural networks, but that's our focus. So before we get into some of the details about constructing neural networks, let's talk about the environment in which you're going to work. So Bioteam is an advocate in many ways of cloud ecosystems. We're very familiar with AWS. It's very secure, it's scalable, and there's a wide variety of services that can be used to develop and deploy artificial intelligence. One of the great advantages there is speed to deployment. But then we're all using content platforms of different kinds these days. Bioteam uses Google Drive. These are great for team access to sort of organizational content, and they can be accessed either through browsers or the built-in APIs. And never forget your laptop. If you're using, for example, software tools such as PyTorch and or TensorFlow for development of AI, um, even though there's not typically a GPU available, those packages can run on the platform. And the advantage there is you can completely customize that environment. It's great for coding, getting started. And then on-premises infrastructure, servers, GPUs, CPUs gives you complete ownership in a way that none of those other approaches can. And typically, these different platforms, these different environments are connected to create some sort of a functional hybrid. An important point to appreciate about these neural networks, about deep learning, is that all the data and all the labels of all your data are going to get transformed into well-structured and fairly large numeric matrices, either integers or floating point numbers. So that might be images, that might be text, that might be highly structured data. Regardless, the learning takes place after pre-processing, and it's occurring over these matrices. What's actually being analyzed and where the patterns are getting recognized are through these enormous matrices. What this implies is that the pre-processing step, which is what the work that takes these raw inputs and converts them into matrices, must retain the information in the raw content. Simultaneously, you want these representations of your data to be compact. For example, and then many details go into this depending on the media type. For example, if you're using with text, the way you chunk text for, from sentences and paragraphs down to words and subwords, which is called tokenization, has to preserve syntax and semantics. And the same thing would be true in any other media type or data type. And then very important consideration goes into the sort of the degree of precision of the floating points in these matrices. What you're trying to do is create a representation that's most highly formative, but doesn't waste degrees of precision, which might mean a lot of costly compute that you don't really need to do. So typically people are using various empirical means to determine the absolute best way to represent that as floating points. So we're not going to get much into the details of model architecture, but consider just the outset, the input and output layers. So the input layer is where your pre-processed data goes into the model as matrices. And then the output layer is highly varied depending on the scientific questions that you are attempting to answer. It might be something very simple like yes, no. This image is or is not a member of a particular binary class. But regardless, what you're going to be thinking about when you're creating your neural network is what should the outputs be, what should the inputs be? And then from that, to a certain extent, the hidden layers are determined. So we're mentioning that the model's architecture has to fit your purpose and your resources. When you're going to get into creating a model or training your model, you're going to be thinking a lot about hyperparameters and metrics. The hyperparameters are primarily the different bells and whistles, the dials that you have that going to determine how training occurs. And the metrics are how you're going to evaluate the correctness, the validity of the training, and then obviously the metrics of that'll be used to determine the inference outputs. And you're also going to be thinking about checkpoints and internal validation as training proceeds. So these checkpoints are typically built into training and are essentially evaluating your metrics as training progresses to make sure everything's progressing in the right directions. And these determinations, meaning the architecture of the model and the hyperparameters, might require significant experimentation and testing on your part in order to determine exactly the right set of values. Really depending on what kind of training you're doing. In some cases, the models might be well established, the approaches might be well established, but if you're dealing with interesting or novel data sets, you might spend a fair amount of time testing and training. So you basically have two options here. You can create a model de novo, or you can use an open weights model and then essentially adapt or change that open weights model according to your input data because it's already been pre-trained. So how do you determine which way to go? First important point would be how much data you have compared to how much data was used to make the model. So very, very roughly speaking, if you say the number of samples is somewhere around 1 to 10% of the amount used to create the open weights model, then you could conceivably use that open weights model and do fine tuning as opposed to creating the model de novo. Then critically, is that open weights model capable of handling your inputs? In other words, can you adapt your inputs through pre-processing to such that it will accept the model's expected input? And then what does the model output? Is it built to answer the sort of scientific and research questions that you want answered? And if the general answers to those two questions is yes, then you're likely going to go to fine tuning. There's a few reasons why that's advantageous, but an important one is there's much less training involved. So quicker, faster, more efficient. So we're trying to sort of simplify sort of a start to finish depiction of creating a model. And this is going to be true whether you're doing fine tuning or de novo creation. You're going to be defining your research questions. You might have to build a data repository. You might have to build a data schema that's going to be used in the standardization process, which is absolutely necessary. So you're going to want highly standardized or harmonized data such that the outputs are and inputs are fairly uniform. Then you're going to make some fundamental decision about where to do the training and pre-processing. If you're using AWS, then SageMaker is a very nice option for that. It's very much an end-to-end sort of data collection all the way to deployment environment and handles a number of different personas. And then we mentioned pre-processing, experimenting with architecture and hyperparameters using some sort of MLOps approaches. So those red boxes, just pointing those out because those steps might take longer than you expect, especially, again, depending on the novelty of your research approach. And thank you very much. I'm enjoying to presenting to you, and keep in touch with us at BioTeam if you have any questions.